Alright, I'm going to help you work through calculation 4. And for calculation 4, I'm using equations that come from the OSHA technical manual. And this was one of the last slides in the calibration lectures. I'm sorry if you missed it. I'll post it so that you can see it and be a little bit more clear on where the calculations are coming from. So from our previous example, we had a time-weighted average of 0.5262 parts per million. That was at 60 degrees Fahrenheit and 630 millimeters of mercury. And we need to convert our parts per million to normal temperature and pressure. So normal temperature and pressure is 760 millimeters mercury and 77 degrees Fahrenheit, which equals 537 degrees Rankine. So you take your Fahrenheit plus 470 to get Rankine. And you need to either be in Rankine or Kelvin when you do pressure and temperature conversions, because you can't have a negative temperature or a negative pressure. And so the formula for so this is our normal temperature and pressure. But we sampled at 60 degrees Fahrenheit and 630 millimeters mercury. So I'm going to take my 60 and add 470 so that I can convert to Rankine, and I'll get 530 degrees Rankine. So the formula for this is parts per million at my sampling conditions equals parts per million normal temperature and pressure times $760 over 630. So what we'd like to adjust to, but what we sampled at, and then we have our 530, what we sampled at, over what we want to adjust to. And now you simply do the math. And over here, this would be 5262 equals. So I'm going to solve the problem for you. I got 760 divided by 630. So I solved this side, 1.2. Now I'm going to multiply by my 530 divided by 537. So now you know if I bring this over here, I'll be able to solve for that variable. My parts per million at normal temperature and pressure. So I just adjusted my 0.5262 parts per million at my sampling conditions to normal temperature and pressure. And now if I want to take that one step further and put it in milligrams per meters cubed, use this equation. So parts per million equals milligrams per meters cubed times 24.45. You can use this equation only when you've adjusted for normal temperature and pressure. Then you're allowed to use the constant over the molecular weight. So to solve this part of the problem, we have 0.5331 equals the molecular weight was given, it was 30. So 0.5331 divide, so I multiply by 30, and I got rid of that variable, and then this was a multiplication, so now I divide by and I was just able to convert, oops, from parts per million to milligrams per meters cubed. I hope that's right.